Welcome to the second episode of our series, Anticipating and Preparing for Fusion Energy. In this, the second episode, we'll be interviewing Dr. Axel Meisen for a second time. In the first episode, we explored just what is fusion and what might we anticipate in terms of its impacts. In this episode, we're exploring the pathway to fusion, how to get ready, but also probing its environmental implications. So welcome, Axel. For our new viewers, please let's start out with a little bit of your background, how it is that you became interested in fusion for energy, the research, and the anticipated social and economic impacts.
Thank you for the opportunity, Perry, and thank you for everybody attending here today. So I became interested in fusion energy in the early parts of this century when I held the chair in foresight at the Alberta Research Council, as it was called at that time. And I was charged with the responsibility to look at opportunities, primarily for Alberta, that were long-term opportunities. And energy clearly surfaced very early in that regard. But it wasn't just the known forms of energy, from hydrocarbons. Solar and geothermal energy came to the forefront as well. But then there was this unusual type of energy, which is now referred to as fusion energy. And in the first instance, I had to distinguish it from fission energy. That didn't take too long to figure out. And I had an opportunity to see the work that was leading towards fusion energy at the National Ignition Facility in California. A small group of us went there, and we recognized the long-term enormous potential that fusion energy could provide. At that time, we weren't that much focused on greenhouse gas emissions, although that started to become part of the conversation. And of course, fusion energy, which is the result of the fusing of light in nuclei, deuterium and tritium are the typical ones that we're looking at, is not accompanied by greenhouse gas emissions of any significance. It is not accompanied by high levels of radioactivity. It has low risk from an explosive runaway nuclear reaction perspective. In fact, it has really no risk with respect to a runaway nuclear meltdown. So these were all very attractive, even though they were far out. And I, of course, pointed out, and it was pointed out to me, and we also started the first episode of this interview with the fact that fusion is the energy that's produced in the sun and in the stars. So it's a natural phenomenon. It's extremely powerful. And the challenge is to harness it on Earth for the benefits of humankind. And that takes us to today.
Well, thank you. I think optimism is high. We're certainly not talking as we once did. It's always 50 years into the future. Capital is flowing, but even though our earlier episode was only a few weeks ago, progress continues. Is there anything new to report by any of the many research labs and now corporations engaged in the race to achieve a sustained fusion reaction?
Well, there have been reports out of Japan and also out of China of the sustaining of plasmas for very significant periods of time, and sustaining plasmas under conditions where fusion can occur is a prerequisite for fusion to occur. So that's very exciting, and there's hardly a week that goes by when some major advance is not reported. So I feel very optimistic from that perspective that we're really making good progress scientifically. My great regret is so far, and this will come out in this conversation, that Canada is not, as of yet, a major participant, even though we have individuals who have expertise and knowledge and approaches who could make enormous contributions. And my hope and my dedication is to enable precisely that.
Even though of late there seems to be some fading interest in a number of policies that have shaped Canada's activities over the last few years, what roles do you see fusion energy playing in helping Canada meet its climate goals and reducing greenhouse gas emissions, say by 2050 and beyond, as seems to be our focus?
Yeah, so I don't think that fusion energy production will be a significant contributor either in Canada or worldwide to the reduction of greenhouse gas emissions. But in the second half of the century, that will become prominent. Because in order to make an impact, you have to have a large number of plants that generate electricity. And if a good sized plant produces between 1 and 3 gigawatts of electricity, uh, for example, that's large for any one plant. But in aggregate, and what the world needs, this is a tiny fraction. So we will need hundreds, ultimately thousands of plants to produce energy from fusion, just as we currently have hundreds, indeed thousands of plants that produce electricity from natural gas or from hydropower. So it will shift over to fusion in the years to come. And we have to work on making that happen. We can't just wait until the second half of the century and then assume that fusion energy will be available. It takes hard, but really very rewarding work to make it happen.
But
And
it's not
that's what we're engaged.
but it's not an unrealistic expectation that it should be recognized as having potential impact on climate.
It will have a big impact on climate, but it is cumulative. I mean, even if you look at the impact of solar energy today, it's still only less than 20% in most countries. Globally, it's about 15% of energy production in total. Now, 15% is a lot more than nothing, but we've come from nothing over the last 20 years with respect to solar, and that will likely increase.
So is the focus for the moment on the last half of the century and the beginning of the deployment of fusion energy on a large scale? Are there environmental and safety risks that should be aware? Any associated with fusion energy production on the large scale?
Yes, there are some safety risks, and we have to identify and face those squarely. So, what are they? They are not explosions or they are not radioactive meltdowns or runaways, mainly because the plasmas are extremely difficult to maintain, to keep on going. But there are some risks because you deal typically with tritium as being one of the fuels. Now, there are other processes that you can use that do not use tritium, but tritium is the favored one. And tritium is a radioactive material. It has a half-life of about 12 years, so it decays fairly rapidly. But it does constitute a health hazard if tritium is incorporated into water, inhaled, for example, it will do damage. So tritium has to be managed. And we know how to manage tritium very well in the case of Canada because it's a byproduct from the CANDU nuclear fission process. And we have handled and we've developed expertise for tritium since the beginning of CANDUs in the 1950s. So that it's a tritium in its radioactivity is one aspect that one has to look at. The other aspect is because the fusion reactions create neutrons, these neutrons have so much energy that they can make certain other materials radioactive. For example, iron can become radioactive, tungsten can become radioactive, and you end then up with materials, and iron and tungsten would typically be used as structural materials in a fusion plant that have to be managed. But the half-lives of the chemicals that I mentioned are short. They run into from a few years to a few decades. So if you store those materials for 100 years, they would lose their radioactivity, which is different from the byproducts that are produced in most fission reactors, some of which have half-lives that run into thousands of years. And therefore, you need these geological storage places that have to be kept and managed over the millennia, not just over several years. So I think those are dangers that have to be looked at, and that's precisely what is being done by the scientists, by the regulators who have become engaged in this.
So when we talk about fusion and its extraordinary implications, I mean, we're looking at a source that can be fueled for billions of years, that can be located within population centers because it's lower risk. Those that study the evolution of energy often note that wood for energy hasn't disappeared, coal for energy hasn't disappeared. We have now hydro, solar, and energy that aren't disappearing. Those that really get excited about fusion, seeing it displacing all this as opposed to complementing, and yet the energy demands of the globe have continued to rise. Do you see it as as displacing these other sources of energy or complementary?
I think in many cases they are complementary, but at times they do displace. And for example, the amount of coal that's used today to generate electricity is significantly below what it used to be in North America. Like Ontario used to, and Alberta used to burn large amounts of coal to generate electricity. That essentially has stopped, been replaced by natural gas as a source of energy. And I think we will likely see the displacement of natural gas by fusion energy in the longer term, which then means, of course, what are we doing with the natural gas that we have? Just like we can ask the question, what do we do with the coal that we currently have? Fortunately, natural gas is somewhat more versatile than coal. I mean, there's coal that you can use for energy purposes and coal that you can use for metallurgical purposes. And the demand for coal for metallurgical purposes hasn't really changed. But there is a connection even there to fusion. If you think about production of steel, which involves coking type of coal, there's a lot of work going on using electricity to convert iron ore into iron. And that electricity can, in principle, come from fusion energy. So you may very well see in the longer term a displacement of coking coal, metallurgical coal by fusion energy as well. And it opens up new opportunities for the steel industry, to use that as an example.
Well, there are many that talk about electrification being a
Yes,
movement in itself. And now with artificial intelligence and the demands made by data centers, which is a whole nother revolution in itself, it's conceivable that fusion is arriving at just the right time, which takes us into the next phase of this discussion, which is marketing.
right.
When I was first exposed to fusion, it looked to me like the engineers and the scientists in academia were pushing fusion. But we know full well if we're ever going to make a full dent or a dent into its commercialization, we need to we need to be able to portray fusion in such a way that there is a demand, a pull for it. So what misconceptions about fusion energy do we encounter most frequently that may be restraining the adoption of fusion or the excitement of the general public?
Well, I think there are several. One of them is this notion that fusion is always a long time away. I think that assumption or preconception is changing, and it is much greater proximity now than it used to be. But that doesn't mean it is available next year. Just as we said at the introduction of this conversation, it will take several decades until fusion will become widely available. But let's go beyond that aspect. Fusion energy production is really difficult to do. And anything that's difficult to do is normally capital intensive. And in many cases, it's uncertain of how to do this. Today, we have three principal ways of fusing light isotopes. Some people would argue there's probably a dozen, but there are three principal ways, the inertial confinement, the magnetic confinement, and the magnetic target approach. And we talked about that the last time. Each one of these is complex with respect to the fusion reactor itself, because you have to get to these extreme conditions of temperatures and pressures and times. But because the fusion is not complete in the reactor, it's only partial, you have to recycle your materials. And so there is this issue of how do you do the recycling? And that's a difficult technical problem. And what you get from a fusion reactor is essentially thermal energy and neutrons. And so you have to convert that thermal energy also into electricity, which is typically the desired product from a fusion plant. Although there are applications that utilize just the high temperatures from a fusion plant. So it's complex to do that, and there are many engineering problems that remain to be solved. I mentioned early on the induced radioactivity into structural materials. You can't let that build up, so you have to change these materials out. So that's an important problem. You have to manage the tritium. When it is being recycled, you have to have enough storage material, and you have to produce the tritium inside the plant by exposing the neutrons to lithium isotopes. So that's a difficult task to do. And we don't have good answers to some of these things. And we certainly don't have good answers to the question of how will a plant like this operate over an extended period of time. When you make a multi-billion-dollar investment in a plant, it's meant to run for a good number of years, taking into account maintenance. You don't want it to fail. So we don't have enough knowledge about that. So that's what makes people rightfully cautious and skeptical, and we have to recognize that. But the only way to deal with that is to work at it.
So most of these issues are issues that an engineer would be familiar with, a physics teacher perhaps, and unlikely to be of particular concern to the general public, that may not be that, quote, sophisticated. Just as with the internal combustion engine, most people buy a car. I'm sorry, most people buy a car. They don't buy an internal combustion engine. And when we get to fusion, moving from market push to market pull, and getting the public generally aware of fusion, they're going to want to know more about its social and an economic relevance.
Right.
So how do we get the general public, including students and teachers, to learn and understand fusion energy, not so much from the engineering perspective, but from the social and economic pros and cons?
So people undoubtedly are interested in the cost of fusion energy, and let's assume that fusion energy manifests itself in the form of electricity. They want to know whether they have to pay 1 cent per kilowatt hour, 10 cents per kilowatt hour, or 100 cents per kilowatt hour. So price is really important. And if fusion energy in the form of electricity cannot be made available in the range of 1 to 20 cents per kilowatt hours, it will not find public acceptance, and the public will look for alternatives. So that's one very important aspect. The other very important aspect is reliability. If you're a purchaser of electricity, you want to be sure that you can count on the electricity being available to you for your personal use or in a hospital or in the company. And that has to be addressed. Then there is the really important issue of who are the men and women who will run these fusion plants. As fusion plants become available, and as we talked a few minutes ago, if other sources of energy are being downsized or maybe even abandoned, how do we make the transition for people to go from one kind of industry, which may be the natural gas or coal industry, into the fusion industry? That's a really important consideration because nobody would like to lose his or her job. But I think the fusion energy sector provides opportunities of a really good working environment, really worthwhile type of work that people will enjoy doing. It's a very sophisticated type of work to be done, and you do it for a good cause, namely providing energy that is so essential for our style of life. In terms of younger people, they typically get excited. Many of them get excited by the science and the difficulties of it. But I also look for, and we in the Fusion Energy Council of Canada, we place a lot of emphasis on prospective students in fields other than engineering and science, like in business. What are the business opportunities? What are the opportunities for chemists who want to use the energy? For metallurgists who might be interested in using electricity in order to make steel, which we talked about just a few moments ago. So fusion energy opens up enormous opportunities. I shouldn't overlook quantum computing and artificial intelligence, which is in the forefront of most of our minds right now. So fusion energy is a tremendous enabler for a better future in terms of making existing products, but also making entirely new products. It will enable us to make products that are very energy intensive, would be too expensive to make with oil and gas, for example, as their sources of energy. And therein, I think, lies a lot of excitement for all members of the public as they become exposed to it.
We haven't touched on one other dimension of energy and which is accessibility. When one thinks about economies, one appreciates most economies, almost all economies have access to energy. Much of the world today still is remote, even though we've had vast movements of urbanization. There are people living, whether they be indigenous or simply be in the vast rural areas of the world. Does fusion offer any potential? Is it going to be more accessible given that it's one of the sources of fuel is water? But do you want to comment at all about whether or not fusion has the potential to be more accessible to more of the world than what we have today?
I think it very clearly has the potential because the raw materials that you need for fusion, if you go with deuterium tritium fusion as the example, are deuterium and lithium in very small quantities. You're talking about 90 kilograms per year of deuterium and maybe 300 kilograms of lithium per year for a gigawatt plant that could supply up to 1 million people. So the transportation of the raw materials to the site is not a major issue. You don't need pipelines. You can, in fact, transport the raw materials by air at a reasonably justifiable cost if you wanted to do that. But that's not to say that the first fusion plants will be located in small communities and in remote communities. I think that's highly unlikely because of the expertise and highly skilled workforce that you do need. And that they are typically more available in urban centers. But over time, that will change. And if you were to look at it from the perspective of a country, take a country like Bolivia, for example. If it were to invest in one or two fusion plants, it could satisfy the energy demand of the entire country.
Mhm.
Uh, and and that's remarkable. So countries that are energy poor and would find it very difficult to justify the ongoing expenditures associated, for example, with natural gas or with petroleum, if they don't have natural gas and petroleum in their own borders. That's where fusion energy can make a very, very big difference.
So this development is more than just engineering. It is recognizing that at some point in time, the public is going to become aware and either be confused or fear or enthusiastic, which obviously those that are champions of fusion want to see a public that's enthusiastic. And so we're calling for public awareness campaigns that may play a role in helping build trust and enthusiasm for fusion. Are these Is it a little bit early to be acquainting the public and developing that level of trust, or do we run the risk of them becoming fearful of something before they really even understand it?
I think we have to be careful about how we inform the public so the public is not misled. And I say to my colleagues in the Fusion Energy Council of Canada, we must be objective advocates of fusion energy, meaning we will present its strengths and we will present its challenges in a fair and balanced way, neither overstating or understating the strengths and the deficiencies. And how to do that is really quite difficult because we live, especially in North America, in an environment where advertising is very common. And if you look at the way people advertise and therefore promote a product, they only accentuate the positive parts. And it makes people feel hesitant, in some cases jaded, to the point where they don't believe what an advertisement says anymore. So I think we want to be really thoughtful and careful about how we present fusion energy. And I'm delighted that you're giving me the opportunity to speak about it in what I would call a balanced way. It has great potential. It takes a lot of work. There are some risks to deal with, but the rewards for society at large are great. And so I think if the public understands the balance, it's important. I think it's also very important that the public understands that people who are currently working in the energy industry and whose companies may be negatively impacted by the advent of fusion energy or solar energy or the other forms, that they're not left behind. And let me make one other comment, which relates to Indigenous community. In Canada, we're very aware and we're really interested in involving Indigenous people in decision making, and that will certainly be the case as we locate fusion plants. What I would like to see and what I've advocated is the involvement of young members of Indigenous communities in educational programs that lead to middle and senior level jobs in the industry, so that we do not create fusion plants where in an area where there may be one or several Indigenous communities, and then the members of the Indigenous communities drive the trucks, staff the cafeteria, but are not the managers or the scientists or the engineers or the business people. And we fortunately have the opportunity and the time to educate or enable the education of Indigenous people with respect to fusion energy. And that's what I think we need to do. So I would like to see nothing better than a number of scholarships, for example, or bursaries for members of Indigenous communities to become acquainted with fusion energy and If we can do that, then we build the workforce of the future for that sector, but integrated with the needs of their communities.
So manpower preparation, marketing, we've talked about a number of the engineering challenges yet before us that relate to containment,
Yes.
the production of the fuel, the tritium, the deuterium. Um, what in the next 20 years, if we're seeing the commercialization of future energy becoming widely available by 2050, and that begins this new period, what societal changes, positive and negative? This is a very, very significant moment of being able to have a billion-year supply of energy accessible, assuming it's cost affordable. It seems to me the changes would be profound. Do you want to elaborate on that element of this?
Yes, I think the most direct positive impact will be on poorer members of society. If they have access to affordable, reliable energy, it will enable them to establish businesses, to grow their businesses. It will enable them to have computing power, which we touched on before. It will enable them to travel and for business or even for pleasure. There's ample evidence to the effect that when energy becomes available at affordable and reliable prices, it can lift entire segments of society from a state of uh, poverty into what we often call the middle class, where they have access to facilities and amenities. And that's really very important to do. So I see it as an enabler in that respect for Canada. But if I look around the world, there are countries that are impoverished as countries and do not have access to affordable energy. If we can make that possible, then we will also improve the lives of people throughout the world. Today, we still have out of 7 billion people, of the order of 2 billion people who don't have access to electricity in any reliable way. And this is remarkable in the 21st century where we are, but we're only making slow progress, and fusion energy should provide one way of addressing that.
Well, this brings us to wrap up, Axel. You focused
Okay.
on the impact of fusion and how it may well aid the lives of individuals in the billions. And it would, I think it's not hard to say as well that it will enable nations today to become more self-sufficient in order to produce what their people need in order to stabilize and provide levels of sufficiency for those nations. So I want to thank you for your input through these 2 episodes. I'm sure we'll be meeting again and discussing this further, but particularly when we get to 2050, and we're both going to be reflecting on fusion at that time. So again, thank you very much for your input today.
Yeah, very welcome, and thank you for the opportunity. Appreciate it.
So Axel, before we move to a Q&A, I would like you to just reflect a little bit on what has taken place in the last 3 weeks. I mean, we've talked about beginning to make progress, and it appears to be almost a weekly event that something significant, I don't mean just incidental, but something significant. Would you reflect, or maybe Alan Offenberger would like to do so? I know he's with us today, but just the progress we've made or we've heard about in the last few weeks.
Well, there's a lot happening in the world, and it's not just politics and it's not just tariffs and other matters of this kind. I would like to point to the fact that as disorganized as the United States may appear to be, and sometimes, some respects it is, the support for fusion seems to be continuing and continuing strongly. General Fusion was just awarded a major contract by the Department of Energy for the production of superconducting magnets using the technologies from CFS, Commonwealth Fusion Systems. I mean, I think this is, in these turbulent economic and political times, a real endorsement of people throughout the United States administration for fusion. Now, there have also been significant advances, scientific and technical advances in China in the last few weeks, which are very positive indeed. So there's, as you mentioned, there's hardly a week that goes by without some significant advances being made, but we need many more of those in order to arrive at an overall fusion energy system. I just wish that Canada would be given an opportunity to participate more strongly in those kinds of advances than what we currently have.
Alan, anything you want to add? I mean, you're monitoring research is certainly as close as Axel. Anything you've picked up on in the last few weeks?
Okay. Well, just a few general comments. Let me put it in context. I started into this field with lasers and the word fusion back in the early 1960s. So we're a few decades longer in the tooth. But when it was, and it was pointed out, when I was a graduate student at MIT, there was a major symposium and Russian speakers were there too, and made the comment, this is going to be the toughest technological nut that we'll ever try and tackle. And indeed, it has been that. But if you look through those decades in terms of scientific theory, modeling, enabling technologies, background materials, just the whole host of all the things you need to bring it together, that learning curve, it's been long, but it's been remarkable. And that to me is just a profound achievement of a lot of people all over the world for over 6 decades. Well, what it has brought us to in the last short while is the fact that people have taken very different approaches to the fusion. And when it was mentioned earlier between magnetic confinement, inertial confinement, alternative technologies, while many of them were done as a sort of a scientific curiosity approach, in fact, many of them are now being picked up and seriously pursued for the commercial fusion. So we've got the learning curve in a wide variety of approaches, not just one. And you could maybe expect failure if you only have one. But in fact, there are many approaches. They're all showing promise. And the upshot is private sector is investing in all of these various approaches to the extent that there's enough confidence from all of the learning curve that yes, many of them could work and should work. So that to me is the big story, is where the science technology has evolved to the current. Money is now being invested. Private sector is getting involved to the tune of billions of dollars. And equally, while governments have funded all of the past decades through their national labs, through academic, through government industrial labs, nevertheless, at this stage, it's moving out into the private sector, and the governments of many countries, the US in particular, UK in particular, Germany and Japan and China, all of them have set up public-private initiatives in order to couple together that which the learning curve produced with those who are now prepared to invest in the future, so that you get a good transmission of all of that information into as short a time frame as possible. The other thing I would maybe make the point on timing is that while the learning curve had to necessarily be long, now that we've got the private sector involved, they won't be quite so patient. They want results faster. And what this will do is put a lot more impetus in solving the various problems that you need to solve along the way. So I feel very, very good about the future. Axel, everybody's right. This is not an overnight solution. There are some companies that are saying they will have solutions in 5 to 10 years. Others say 15 years, and others say a longer time. But there is a spectrum of time frames there, and we'll be able to measure it in a fairly short, very short interval. So this, I think, is promising. And with the public-private get together, I expect a lot of problems to be solved. Related to the public-private, as already mentioned by Axel, you've got the issue of a number of underlying common themes. Because if you were looking to go out and build a reactor today and you ask the question, how much could I buy off the shelf versus have to further develop? The answer is it's a spectrum. You might be able to go out and buy 50, 60% of the stuff off the shelf. But some things are going to take a few years to scale up into manufacturing. Other things are going to take up to a decade to scale up in manufacturing in order to have all the pieces in hand. It's your supply chain. But this is being worked on. There are a lot of other companies outside of the frontline fusion companies with background technology related expertise that are already working and getting involved. So I expect a lot of this to become moving together quite quickly and efficiently.
Well, I'm going to interrupt
Um,
here just for a second.
yep.
Uh, it's very hard to get into a discussion that doesn't use the word profound in terms of the impact of these technologies. It's incredibly interesting to look at the science and to look at the engineering. I am equally afraid of the lack of attention to the profound impact socially and economically of this technology on our society. I hear engineers and I hear scientists and I hear capitalists and I hear investors all excited about the technology. I hear almost no one, and Axel, with your exception, uh, talking about what does this mean to the poor? What does this mean to nations that have relied on energy for their economies? If this is that profound, is anybody spending time looking at how profound an impact this tsunami could be on the status quo? Who cares? Where do I find the professor emeritus of fusion impact?
Oh, you're provocative.
Well, yeah, you're looking at a couple of them.
But I am serious.
Yeah,
I mean, you
Yeah,
you you've
you're
done
right.
you've done such an extraordinary job exciting the world about the prospect of the wheel of fire, of an infinite amount of energy to for our economies, for our society to be transformed. And yet, I don't know where the regulatory forces are. I don't know where the manpower training is coming for. I don't know about the powers. I know nothing about the social and economic implications of this, and it scares me.
Well, just a quick reply. I would make the case no need to be scared, but we're just at that jumping off moment. So now is the time. You don't have to have worried that 10 or 20 years ago we should have been doing all of this. I
But
think
where,
it was the appropriate time to start that larger
but
educational process, and it
last
is taking place.
okay, 5 years ago it was 50 years. 2 years ago it was 2050. I hear this week it's now going to be 2030, and yet we still haven't started.
Well, I think your seminars, and as we move these broadcasts out, we will reach a larger audience all the time. FECC is trying to do it through students, through connections with all the other organizations in the country and externally. And you're finding the same in other organizations. The news is now starting to spin up that if you take in the US as the biggest nation involved through their nuclear societies, they're now moving into this sphere of advertising, educating, making awareness, looking for the feedback from society. What are the social implications that we need to be concerned about? So
Okay.
we are at a jumping off point that I think you'll see a lot more done in the next 5 years.
Well, just to reinforce it's important. I mean, Axel, I'll ask you to elaborate on this point. You made reference to the fact that if we get this off on the wrong foot, if people start equating this with some of the negatives of nuclear, if people start worrying about whether this technology is safe or not, and they're not well educated. We run the risk of somebody of having, particularly in an activist world, we run the risk of somebody becoming Luddites and fighting this. Axel?
That's possible, but I take a lot of encouragement from our academic colleagues, particularly in countries like the United States, which have had fusion energy programs. If you look at the young men and women, and I include in that faculty members at MIT, for example, the people in Dennis White's group at MIT, they're extremely good and effective spokespersons for fusion energy. When I look at somebody like Steffi Deem at the University of Wisconsin, she is a wonderful interlocutor for fusion energy, not only for engineering and science students, but for members of the public at large. In Canada, we haven't had the good fortune of academic people being funded to do work in fusion in a consistent and coherent way. So that's one of the things that we really must achieve. Now, persons like Alan and Robert Fotiseus, are very good ambassadors, not only for other scientists and engineers, but for communities at large. And they take a lot of time and spend a lot of time achieving that. But much more needs to be done. Fortunately, I think that in the case of fusion, the inherent risks and dangers are so much less than they are in other areas of energy production. So that's helpful.
I agree with you. And I think so often we look at the risks from an engineering perspective. I'm looking at the risks from an economic and social disruption.
Well, that's why we need to place emphasis on the opportunities that a wealth of energy gives. That's why we need to find ways to enable people to transition from their existing industries into the fusion energy industry, as well as those industries that the fusion energy industry will supply. And, as a country, we are not as good as that at doing that as, for example, the Nordic countries are. If you look at the transitions in the workforce that have taken place in countries like Sweden, Norway, Denmark, I would include the Netherlands as well, from traditional industries into new industries, so that people in mid-career are not left behind. They have much to say and they have much to demonstrate. And that's what we need to do as well. In Canada, we have the special challenge of Indigenous people who are often in remote areas, and we must include them as well.
So if there's any nation in the world that could benefit more than Canada, I don't know which one it is from the perspective of how much of this country is still waiting for energy. One for economic reasons, which is the North, or for its indigenous population, which is the North. No, most of Canada does not have access to energy, and yet most of Canada is about $3 trillion worth of undeveloped economy. So if there's anything Canada could do in terms of pulling fusion into the future, whether it be our oil sands or the undiscovered and undeveloped North, it's Canada. There is the opportunity for pull. We've got some questions, and they do relate to some extent to the engineering. Some of the technical challenges that lie ahead. I think we've elaborated on that in the past, but what right now, Alan, I'll throw this at you. What do you see as the major hurdles right now for commercialization from an engineering point of view?
The first of all will be scaling up smaller experimental devices to demonstration capability. And some of those tasks are underway now, but that is a key next step. In the course of doing that, it will bring out the issues of all of the related technologies and the developments needed. Materials, to me, is just the fundamental underlying issue. If you can sort out the materials, you'll be well on your way. The other is going to be the tritium fuels in that, just to illustrate the point, if you take the magnetic confinement approach, the burn-up rate of the tritium is only a few percent. So it means that you've got to have an inventory to always replenish your fuel when it's such a small burn-up rate. If you have inertial, the burn-up rate is going to be at least 30%. So it's less of a problem, but it is the problem in all cases. So you've got to come up with all of the fuel generation, recycling, processing, handling to make that work to keep the tritium supply sufficient. Materials insofar as neutrons can radioactivate, you're going to want to work on, and people are working on alternatives to tungsten, vanadium steels. We'd love to have the silicon carbides are a beautiful thing that would never be radioactivated in the first place. It's just that we don't know how to make them in large quantities, large sheets, to use that as the structural material. So this work is being pursued as well. So you want materials ideally that are not going to be problematic, but on the way there, you'll work with materials that are. As Axel has already mentioned, these tend to have relatively short radioactive decay times, tens of years, so you can bury them, dig them up, and reprocess them. But you're going to want to do the engineering in a way that if I don't want to have to shut a machine down for a long extended period to replace materials, I'm going to want to have a wheel in, wheel out process where I just out on tracks, I take out one working device, put in another, and I'm shut down for a very limited time. So there's a whole series of systems operations that need to be addressed, materials, and these are common to all of the approaches, as well as the tritium fuels. And then, of course, the individual approaches will demand certain kinds of instrumentations and controls that have to be solved particular to that kind of device. So that's some of the issues, and it's going to take time.
Anything you want to add there, Axel?
Well, I would say there are many job opportunities that are not of a technical nature. One area that I've often pointed to because it gets overlooked is the insurance industry. If you have a plant that's worth $1 billion, that's a commercial entity, it needs to be insured. And that means you have to have men and women who understand the technology, who understand the technical and the business and the other types of risks. So it's a great opportunity for people who are interested in risk management, risk assessment, and insurance. And I have reached out to the nuclear insurance industry of Canada, which is primarily focused on fission, to take an interest in fusion. And they're starting to take an interest now because they can see from reading and listening that commercial fusion plants are not that far into the future, and they need to prepare their people. So there's a good set of job opportunities.
And that's a form of what we're referring to as the pull versus the push.
Right.
Are there any projects being developed that are what are called aneutronic fusion, lithium reactant, boron, deuterium retreat? Is there anything other than what we've typically been talking about as neutron-based fusion?
Yeah,
Yeah,
so
yes, there are. Yep.
most of the emphasis has been on deuterium and tritium because as difficult as it is, relatively speaking, it is easier than some of the others. So hydrogen boron, Hb12 is the other good example. It's not entirely free of neutrons, but it is much closer to being free of neutrons. Alan, but you may wish to comment.
Yeah, it's there are a few companies that are pursuing that approach. The attraction being there's US, New Zealand, Australia, around the world we have a few companies looking at what are called aneutronic, where the fuel proton, boron, and so on primarily gives you charged particles that you could then do direct electrical conversion. These are intrinsically more difficult, though, because you need much higher temperature. And traditionally, and I think you will find commercially, the initial fusion systems will tend to run on deuterium tritium. It has the lowest ignition temperature. And if I've got to go up to 10 times that temperature, I'd better go through a learning curve, the easier routing to get to where I want in the long run. So I think we will concentrate on the deuterium tritium, get the learning curve, and eventually with deuterium and then on work to higher temperatures and other alternative approaches.
You can think in terms of analogies, right? The first airplanes had piston engines. They evolved to turboprop engines and then into jet engines. And jet engines were not feasible in the 1920s because of the lack of the right materials and various other reasons. So I think there's that progression that takes place. But even today, there are still piston powered planes around, and they have a niche. And I'm sure the deuterium tritium will have a niche in the fusion world for many, many years to come.
Yeah.
So this isn't Las Vegas, this is Edmonton. If you wanted to gamble, is there any technology that you think right now, given what we know or what we think will emerge, that looks like it's more advanced and has a higher probability? I mean, Alan, that was a question you and I pursued some years ago, was when we looked at general fusion and went down to California to deliver more. You know, we all had some sense of what was winning the race. Any sense today of what is further ahead than another?
Well, from the point of view of having developed out of a learning curve on the tokamak, the tokamak device that was first conceived of by the Russians, it's had the largest investment in learning curve over the decades. I would probably give it a slight edge for two reasons. One is that learning curve and knowledge base, and for two, new technology out of MIT that has allowed this company called Commonwealth Fusion Systems to actually get investments up to a couple of $1 billion. And they have also chosen a site to build a first reactor in North Carolina. It's where all the large data centers are, and they want large amounts of energy. So they have now arranged to put their first demonstration there. Their operating plant is in Fort Devens in Massachusetts, out of which they're building the technology and demo plants themselves. But the first commercial plant is meant to go into North Carolina. So, and with all the resources and the investment and the learning curve, as I say, they're probably as far ahead as anybody's going to be. But that begs the question of what approach would you like if you could have your druthers? And I'm still a fan of the inertial fusion for two reasons. One is that in terms of scientific demonstration, the inertial is the only technology so far that's actually produced a scientific demonstration of net energy gain. And the technology has progressed remarkably fast, primarily through military funding in countries that wanted to have a means of weapons testing without exploding bombs in the air. And so they went at the laser fusion approach to find a way of doing laboratory testing to maintain their weapons. This learning curve has been very rapid indeed, far faster than even of the magnetic fusion. And so given the investment and the approaches, and then what potentially could be the benefits of the inertial, in that you can isolate your chamber from your drivers, from your fuel, and have a lot more control on maintenance, if you will, of a system. It has a number of really attractive things as far as I'm concerned. So if you were to take the Commonwealth Fusion tokamak, coupled with the inertial and the laser firms going out to do scale up to drive commercial energy there, coupled with a couple of intermediaries, one of them being General Fusion, because they've had a long learning curve now and healthy investment with their approach, which is different. And another one in the US, Helion in Washington State, which has yet another different approach, but a lot of investment to bring their learning curve up as well. So I'd say there's probably about 4 that are nearer term on the horizon to demonstrate this commercial feasibility.
Okay, well, that's a good wrap-up question on the technical side. I'm going to look for a show of hands to see if there are any outstanding questions yet of either Axel or Alan. And if not, go ahead, Peter.
Well, I have a few questions. I guess I posted them. I think one of them has more or less been answered about kind of parts of the supply chain. So what I was wondering is what are the current metallurgical limits, temperature-wise, in the durability of confinement chambers for either a magnetic or inertial or any other combination of these in terms of building the actual physical plants and being in a mode of commercially productive?
I'll try a bit of an answer. We haven't got the full answer yet because we don't have the big devices yet operating to put that full neutron flux on the materials. So in part, there isn't an answer, but in part, en route to ITER, this large international project in France, materials are a very big part of the agenda there. And they're looking at tungsten and various coated versions. But the biggest worrying is not so much the thermal as the neutron impact, because apart from radioactivity, you actually do structural damage. So you start to generate voids and structural breakdown, and you get helium production building up inside the material, and that leads to finite lifetime as well. So what we really need is an operating device at the full scale, sort of 10 to the 14 neutrons per square centimeter per second coming out at you to really get the answers on the materials. But from all of the theory that's been done in small scale experimental studies, a significant amount, of course, at Oak Ridge National Labs, they've traditionally been a materials science center in everything, let alone fusion. We can pinpoint where the problems are likely to surface, and now what we need is these advanced materials to be put in front of a big neutron flux. So we really need the heater up and running.
It is the hydrogen that gets into the metal
as well.
Is that coming from a release in the metal itself, or is it coming from the plasma, or some interaction between them?
And hydrogen isn't as big a problem as helium, in fact, because the neutrons coming out.
Yeah, sorry, I meant helium, but
yeah, helium, yeah.
Both gases.
So it's the plasma source, if you will, it's going to generate the biggest problem. Yeah.
Yes. Okay.
Okay. Well,
but over time, hydrogen also has an effect because it's quite an aggressive chemical. It's not what shows up over a few days, but it will show up over the normal life of a plant between ordinary shutdowns, which you like to have occur no more frequently than a year. But that's an aspirational aspect. So that's what Alan said early on, the ability to swap out components quickly without impairing your production of electricity becomes so important. So there's a whole host of things that would show up only on a larger scale, and when you do the test over longer periods of time.
Yeah. So we compare that, say, to operating fission facilities today, like Gen 3 type reactors. They can go for decades without serious issues, and they're operated correctly. So would fusion try to be aiming at that? I mean, if the material stability is still a big issue, how do we see that evolving in a time frame? And when you get to a fusion plant, you go say this is good for 20 years or 10 years or 50 years, or we have any idea yet?
Well, that's what you aim for, because that's what you aim for, and that's what the economics actually dictate. You can't run a multi-billion-dollar plant that is not functioning periodically for longer periods of time. And it doesn't matter that that's a petroleum refinery or a natural gas-fired plant or a fusion plant or a fission plant for that matter.
Thank you.
Okay, well, we are to wrap up. I mean, these have been two fact-filled episodes of anticipating the emergence of fusion and also preparing for its arrival and addressing the pros, the cons, and what needs to be done to move from a push to a pull. I'm going to ask Axel if there's any wrapping comments or wrap-up comments you'd like to make to the group.
Well, I'd like to thank the members of the group for their interest, and I'd particularly like to thank you and Alan for it. I think there is one area that we should think about, and that is new processes, new applications that could be enabled by fusion energy if it were available at lower costs and in the right quantities. I think there are many opportunities in that space, and they haven't been looked at because they're not really within the space of what the plasma physicists or even the chemical engineers and mechanical engineers in the fusion plants do. But it's the application of fusion energy in areas other than the ones that we know about, which is the general grid applications, certain industries like the aluminum industry, or the emerging ones like artificial intelligence and quantum computing. But there are other areas that one can look at, and I'd really like us to do that.
Well, if you like to draw curves and you see an emerging technology like what data centers are drawing on and the development of data centers today to handle everything from quantum to artificial intelligence, it's almost as if this is a partnership, this is a marriage, that one technology is going to be pulling the other. And it certainly looks like the drive and the demands for artificial intelligence will in fact be pulling these extraordinary sources of energy. So we're watching, we're waiting. It used to be 50 years away, then it was 2050, and now we hear almost weekly we could be seeing in 2030. Be reflecting on fusion at that time. So again, thank you very much for your input today.
Yeah, very welcome, and thank you for the opportunity. Appreciate it.